The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so I've got quiz 2 to give back to you with good scores. So it's Christmas early, or good work on that exam. That's fine. And so we all know Fourier series is like a central topic on the final third of the course. And I'll just keep going on Fourier series. I'll give you a homework on 4.1 and 4.2. So 4.1 is what we complete today, the Fourier series. 4.2 is the discrete Fourier series. So those are two major topics for this part of the course. This is the periodic one, and 4.2 will be the finite one with the Fourier matrix showing up. Okay, so can I pick up? I made a list of topics last time that were important for 4.1 for Fourier series, and I think these are the remaining entries on the list. I did the Fourier series for the odd square wave, the -1 stepping up to +1. And you remember that, well, let me put that example down here. That was the step function. Easier if I draw it than if I try to write equations. So it was -1 up to +1 at ending at, of course, period 2 pi. And I guess we called that S of x for S signaling step function, S signaling square wave, and S the general signal that the function is odd. And that means that it goes with sine functions. And I think the amounts, the numbers that we found from the formula was sine x over 1, sine 3x over 3, sine 5x over 5. It's just a great one to remember. Yeah, and that's the example that has the important, and I don't know if I wrote down Gibbs' name. He was the great physicist at Yale, well, 100 years ago or more, and did this key idea that appears all the time, that anytime you have a step function, then the Fourier series has, well, it does its best. If I take 1,000 terms, it'll do its best, but it will overshoot by an amount that Gibbs found, and then it will get really close, and then it will overshoot again, and then symmetrically, or anti-symmetrically, I should say. So that's the Gibbs phenomenon of great importance. Okay. I write this one out because, first, it's an important one to remember. Second, it'll give us a good example for this important equality, that the energy in the function is the energy in the coefficients. That'll be good. Okay. Actually, maybe I should do that one first, because the delta function has got infinite energy, and we don't learn anything from this equation. So let me jump to the energy in the function and the energy in the coefficients. So what do I mean by energy? Well, it's quadratic, right? It's the length squared here. It's the length squared of the function. So let me compute. Maybe I'll do it on this board underneath and leave space for the delta function. The energy in x space is just the integral. It's the length squared. The integral of S of x squared dx. It's just what you would expect. We have a function, not a vector. So we can't sum coefficients squared. Instead, we integrate all the values squared. And of course, this is a number that we can quickly compute for that function. So what does it turn out to be? Well, what is s of x squared for that function? 1, obviously. The function is 1 here. I'm looking at the original s of x, not the series. The function is 1 there and minus 1 there. When I square those, it's s of x squared is 1 everywhere, so I'm integrating 1 everywhere from minus pi to pi, so I get the answer 2 pi. So that's a case where the energy in the physical space, the x space, was totally easy to compute. Now what about energy? What is this equality, this really neat, easy to remember equality? I'm just going to find it by taking this thing squared. What's the integral of the right-hand side? The two are equal. So suppose I just fire away. I integrate the square of that infinite series. You're going to say, well, that's going to take a while. But what's going to be good? The key point, the first point in last time's lecture, the first point in every discussion of Fourier series is orthogonality. Sines times other sines integrated are 0. So a whole lot of terms will go. So I take that thing, I square it. So let me do that one here, the integral from minus pi to pi. May I take out the 4 over pi squared? Just so I don't have it, so it's not confusing. Now this is the sine x over 1, sine 3x over 3, sine kx over k, and so on. All squared, dx. And so what do I get? The 4 over pi squared. And now I've got a whole lot of terms. But the thing is, I can do this. Because when I square this, I'll have a lot of terms like sine x, sine 3x. And when I integrate those, I get 0. So the only ones that I don't get 0 are when sine x integrates against itself and sine 3x against itself. So when sine x integrates against itself, that's sine squared. Its integral is, do you remember the integral of sine squared, which is its average value is 1/2. We're over an interval. I think I'm going to get pi for sine squared. Because sine squared, we could do that calculation separately. It's a standard integral. The integral of sine squared is pi. Actually, yeah, it just uses the fact that sine squared x is the same as whatever it is the same as. Is it 1 minus cosine 2x or something over 2 or plus? Who cares? Because because the integral of whichever, plus or minus, well, I suppose for history's sake, we should get it right. Which is it? Is it a minus? So it looks okay now? Okay. All right. If it's wrong, I didn't say it's wrong. Okay, but I'm going to integrate. So the integral of the cosine is 0, and the integral of the 1/2 is the part I'm talking about. That 1/2 is there all the way from minus pi to pi. So I get a pi from all these signs. And now what are all the terms? Well, 1 over 1 squared. That just had a coefficient 1. But what's the next guy? You remember, I'm squaring it. I'm integrating. But I have a 1 over 3 squared. And 1 over 5 squared. And so on. OK. And here's the great point. These two are equal. I've got the same function expressed in x space, and here it's expressed in sine space, you could say, in harmonic space. OK, so that's equal. And that's going to be the fact in general, that the integral of s of x squared. I mean, so the general fact will be the integral of s of x. Well, I'll write it down below. But let's just see what we get for numbers here. So I had pi on both sides. And so if I lift that over there, I get something like, what do I have? Pi squared over 16. Maybe I have pi squared over 8. You just get like an amazing, a remarkable formula. Putting that up there would be pi squared over 16, and the 2 makes it an 8. And here I have the sum of 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared. So, you know, that's an infinite sum that I would not have known how to do, except it appears here. The sum of 1 over all those squareds. If I picked another example, I could get the sum. Oh, this was all the odd numbers squared. If I picked a different function, I could have got one that had all that also had the sine 2x over 2 and the sine 4x over 4. So this would have been the sum of all the squares. Do you happen to know what that comes out to be? I mean, here's a way to compute pi. We have a formula for pi here. And we'd have another formula that involved all the funds. Maybe I have room for it up here. This would be the sum of 1 over n squared, right? If I had all this here, I have only the odd ones, and I get pi squared over 8. Do you happen to know what I get for all of them? So I'm also including 1 over 2 squared. There's a quarter also in here, and also a 16th, and also a 36th in this one. And the answer happens to be pi squared over 6. Pi squared over 6. Yeah. So it's nice. I mean, the important point about this energy equality is not being able to get a few very remarkable formulas for pi. And there's be another remarkable formula in the homework. But this is a little famous. Do you know what this is? This is the famous Riemann zeta function. The sum of 1 over n to the x is the zeta function at x. Here's the zeta function at 2. So if I could draw a zeta, maybe there's some Greek guys in this class who could do it properly. But anyway, look, I'll chicken out. Zeta of at the value 2, right? Zeta of 2. So we know zeta of 2. We know zeta of 4. I don't think we know zeta of 3. It doesn't come. It's not I think it's not a special number like pi squared over 6. So the zeta function, the sum over 1 to the 1 over n to this thing is that's the subject of a problem that Riemann did not solve. There's a problem Riemann did not solve, and nobody has succeeded to solve it since. There's a $1 million prize for its solution. My neighbors think I should be working on this, but I know better. It's going to be solved one day, but it's pretty difficult. And that is to know where this zeta function, where it's 0. Of course, it isn't 0 at 2, because it's pi squared over 6. And actually, the conjecture is that it's 0. All the zeros are at points, complex numbers with real part a half. So they're on this famous line, the imaginary line with real part a half. And that's the most important problem in pure mathematics, actually. Yeah. So here we go. We got a formula for pi out of this energy identity. And I'll write it again once I have the complex form. Okay. So, but you see where it comes from. It just comes from orthogonality. The fact that we could integrate that square is what made it all work. Okay, let's do the delta function. Okay, so that's an even function. The delta, right? Now I'm looking at the delta function. minus pi to pi. It has the spike at 0, and it's certainly even, so we expect cosines. And what are the coefficients? So it's just an important one to know. Very important example. So what's A naught in general? The coefficient A naught in the Fourier series is if I have a function, delta of x, s of x, whatever my function, the A naught coefficient is the average. A for average there. A naught is the average value. So this is 1 over 2 pi, the integral from minus pi to pi of my function. Where did that come from? I just integrated. I just multiplied both sides by 1 or by 1 over 2 pi and integrated. And all those terms disappeared, and I was left with A naught. And what's the answer? Everybody knows that integral. The integral of the delta function is 1. So I just get 1 over 2 pi. So 1 over 2 pi. Okay, now ready for A1. How much of cosine x do I have? Can I just change this formula to give me A1? And you can tell me what it gives? Well, let me do it here. Here's A1. What's the formula for A1? It's just like B1, like the sine formulas. You have to remember you're only dividing by pi because that average value was a half, as we saw. And then you have the integral of whatever your function is, delta of x in this case, times the cosine of 1x. If we're looking for A1, we've multiplied both sides by cos x and integrated. And what answer do we get for A1? What's the integral of delta of x times cosine x? dx. So I should put in a dx. And the answer is 1, also 1. The delta function, this spike, picks out the value of this function at the spike. Because, of course, it doesn't matter what that function is away from the spike because the other factor, delta, is 0. Everything is at that spike, all the action. And this happens to be 1 at the spike, so I get a 1 over pi. And actually, the same formula for all these guys. This will be the same with cos x changed to cos 2x. And what will be the answer now? Again, 1, right? It's the value, this integral. The formula for A2 would have come by multiplying both sides by cos 2x, integrating, and the integral of cos squared would give me the pi, and I'm dividing by the pi, and I just need that integral, and it's easy. It's also 1 over pi. So all these are 1 over pi. Let me just put in the formula. 1 over 2 pi, and all the rest are 1 over pi. Cos 3x. All the cosines are there, all in the same amount, and the constant term is slightly different. Okay, that's the formal Fourier series for the delta function. Formal meaning you can use it to compute. Of course, some things will fail, like what's the energy? If I try to do energy in x space of the delta function or energy in k space, what answer would I get? Well, the integral of delta squared, its energy, is infinite, right? The integral of delta, if I have delta times delta, then I'm really in trouble, right? Because this delta says, well, if I can speak informally, that delta says take the value of this function at 0, but of course that's infinite. So that would be infinite. That would be the energy in x space. What about the energy in k space? Well, let's think what's the energy in k space. I'm going to do the squares of the coefficients. You remember that's what I had down here? And I'll have it again in a moment. It's the sum of the squares of the coefficients fixed up by factors of pi. And here all the coefficients are constant. So that sum is infinite again. It's the sum of squares of constant, 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 and that series doesn't converge, it blows up. So the energy is infinite. That's okay. The key is that formula. Okay. There's the formula to remember. There's the formula. On forever. Every frequency is in here to the same amount. Yeah, okay. Good. That's the delta function example. Okay, ready to go to complex? Yeah, complex is no big deal. Because we know, actually, you can tell me the complex series for the delta function, I'll write it right underneath. The complex series for the delta function, just turn these guys into e to the I theta, e to the I x's, and e to the I 2x's, and e to the I, e to the minus I 2x's. Just term by term, just to see it, see it clearly for this great example. So what does cosine 2x look like in terms of complex exponentials? Everybody knows cos x is the same as e to the I x and e to the minus I x, right? Divided by 2, because this is cos x plus I sine x. This is cos x minus I sine x. When I add them, I get 2 cosine x's, so I must divide by 2. Let me divide by 2 all the way. So I'm dividing this 1 over pi by 2. You'll see it's so much nicer. So 1 over 2 pi times the 1, that's our first guy. And now I've got the next guy. Right? Because I need to divide by the 2 to get the cosine, and there's my 2. Okay, what's the next? What do I have next? From this guy. 1 over pi, still there. What's cosine of 2x if I want to write it in terms of complex exponentials? So this guy now, I'm ready for him, is e to the I 2x and e to the minus I 2x. Divided by 2, and there's my 2. Do you see what's happening? It's like, there's an example to show you why the complex case is so nice. Here we had to remember a different number for A naught. Here it's just, so the next one will be e to the I 3x and e to the minus I 3x. So the delta function in the complex Fourier series, all the terms have coefficients 1 divided by the 2 pi. That's a great example. Great example, yeah. And of course, we see again that the sum of squares. Oh yeah, yeah. So let's do the complex formula. The complex formula, by which I mean I'm taking any function f, not necessarily even, not necessarily odd, not necessarily real. Any function, it can now be a complex function because we're going to use complex things here. So I'll have all the complex exponentials for integer k. This k is an integer, but it can go from minus infinity to infinity. That's the complex form. F of x is is a series again. The beauty is that every term looks the same. The thing you have to remember is that negative k is allowed as well as positive k. You see that we needed the negative k to get cosines. K was minus 1 there, k was minus 2 there, and for sines we would also need them. So cosines go into it, sines go into it, f of x could be complex. That's the complex series. So maybe we could have started with that series, but we didn't. We came to it here. But what's the formula for its coefficients? Okay, actually, for the next half hour now, we have to think complex. And that will bring a few changes. So watch for the changes. You see that we're almost in the same ballpark. But there are a couple of things to notice. So let me write down that series again. Minus infinity to infinity of some coefficient e to the I kx. Now, what is ck? What is the formula for ck? As soon as we answer that question, you'll see the new aspect for complex. How do I find coefficients? I multiply by something, I integrate, and I use orthogonality. Always. Same ideas. Just repeat after repeat. The question is, what do I multiply by? If I wanted to know C3, suppose I want to know a formula for C3, the coefficient. What am I going to multiply by? That's going to give me the orthogonality I need, that all the other integrals are going to disappear. That's the key. I want to multiply by something so that when I integrate, all the other integrals are going to disappear. And let's just do it. Here, suppose I have e to the I 5x, and I would like that. I'm looking for I'm looking for C3. So I'll look at e to the I 3x. So watch. This is the small point we have to make. So I'm looking for the e to the I 3x. So I'm going to multiply by something, and I'm going to integrate. And what would be the good thing to multiply by? Well, you would say, if you were just a real person, you would say, multiply by e to the I 3x, integrate, and hope for getting 0. You won't get 0. If I multiply e to the I 3x, I'm sorry, you might say, what am I doing here? I'm trying to check orthogonality. Let me instead of 3 use kx. Okay. So that's a typical complex one. It's any one of these guys. And I would like to multiply it. I want to see what's orthogonality. That's what I'm asking. Everything hinged on orthogonality. We've got to have orthogonality here. But let me show you what it is. The thing you multiply by to get the C3 is not e to the I 3x. It is e to the minus I 3x. You take the conjugate. You change I to minus I in the complex case. So if I take e to the I kx times e to the minus I lx, and notice that minus, I claim that I get 0. Except if k is L. Or I get, and when k is L, I get 2 pi if k is L. I get 0 if k is not L. That's the beautiful orthogonality. I'm not too worried about the 2 pi. I'll figure that out. So what I'm saying is, when you're taking inner products, dot products, and you've got complex stuff, one of the factors has to take the complex conjugate. Change I to minus I. Do you see that we've got a completely easy integral now? What is the integral of this guy? How do I see that I really get 0? So this is the first time I'm actually doing an integration and seeing orthogonality. Anybody likes integrating these things because they're so simple to integrate. What's the integral of, if I just, before I plug in the limits, what's the integral of this guy? How do I rewrite that to integrate it easily? I put the two exponents together. This is the same as e to the I k minus Lx, right? The exponentials follow that rule. If I multiply exponentials, I combine the exponents. And now I'm ready to integrate. And so what is the integral of e to the I k minus Lx? When I integrate e to the something x, I get that same thing again divided by the something. Right? So now I've integrated, and now I just want to go from 0 to 2 pi. Plug in the limits from x equals 0 to x equal 2 pi. This is what the integral is asking me for. So I'm actually doing the integral here. I put these together into that. I integrated, which just brought this term down below because the derivative will bring that term above.
Why did the integration limits change?
Oh, they weren't meant to change. They actually, it's wrong but right to change those integration limits. I mean, any 2 pi would work, but thank you. You're totally right. I should have done minus pi to pi. Why do we get 0? That's the whole point. Here we actually did the integral, and we can just plug in x equal pi and x equal minus pi, or we could plug in 0 and 2 pi, or I could plug in any guys that were 2 pi apart, any period of 2 pi. Why do we get 0? Do you have to do the plugging in part to see it? You can, certainly. But the point is, this function is periodic. That's a function that has period 2 pi, so it has to be the same at the lower and the upper limits. That's what it's coming to. That's a periodic function. It's equal at these two limits, and therefore when I do the subtraction I take it at the top limit minus the answer at the bottom limit. It's the same at both, so I get 0. So there is the actual check of orthogonality. So the key point was orthogonality or inner product for complex functions. One of them has to take the complex conjugate. Let me just do for vectors too. Complex vectors. I may have mentioned, let me take the vector 1i as an extreme example. And suppose I wanted to find the inner product with itself, which will be the length squared. What's the inner product of that vector, that complex vector 1i with itself? Let me just raise it up so we see it. Focus on this. Usually the length squared would be 1 squared plus I squared. No good. Why no good? Because it's 0. 1 squared plus I squared is 0. It's just, we want absolute values squared. Absolute values, we need squares. We need positive number here. So the length of this squared, so let me call that vector v. I want to take not v transpose v. That's the thing that would give me 0 if I did 1i. I have to take the complex conjugate. One of the two factors, and it's just a matter of convention which one you do, this is the thing that gives me the length of v squared. And it's the same thing for functions. It's the integral of f of x. Do you want me to write it as it's the integral of f of x times its conjugate that gives me the length of f squared. And of course I can rewrite that as the integral of f, right? We have this handy notation for f times its conjugate it's like r e to the I theta times r e to the minus I theta, the product of r e to the I theta times r e to the minus I theta is what? This is the function, this is the complex number, this is its conjugate. When I multiply, you notice that I went to minus I. When I drop below the imaginary axis, the real axis, I just change I to minus I. So those cancel, and I get R squared. The length, the size of the number. It's just, if you haven't thought complex, just make this change and you're ready to go. Yeah, just V bar transpose V, F bar transpose F, if you like, or F squared. So, and when we make the correct change, we still have the orthogonality. Okay? So that's what orthogonality is. Now, what's the coefficient? So now, after all that speech, tell me, what do I multiply both sides by? Let me start again and remember here. So my f of x is going to be the sum of ck e to the I kx. And if I want to get a coefficient, I'm looking for a formula for C3. So how do I find C3? Let me slow down a second. How to find C3? Multiply both sides by what? And integrate. And integrate minus pi to pi. What goes there? If I want C3, I should multiply both sides by, should I multiply both sides by e to the I3x? Nope. E to the minus I3x. Multiply both sides by e to the minus I3x and integrate. E to the minus I3x dx. And then on the right side, I get what? I get C3, because that'll be e to the minus I3x times e to the plus I3x. I'll be integrating 1, so I'll get a 2 pi, and all zeros from all the other terms. Orthogonality, doing its job again. All these zeros from by orthogonality. By orthogonality. By exactly this integration that we did. If k is 3 and L is 7, or k is 7 and L is 3, the integral gives 0. So what's the formula then? This is all gone. Divide by 2 pi, and you've got it. There you are. That's the coefficient. Okay. We have to move to complex numbers, and now in those 20 minutes, we've got the only change to make is conjugate one of the things when it can be complex. Okay, good. So that's the complex series. What's the energy inequality now? Let me do the energy equality in x space and in k space. If I take this, now so that's an equality of two functions. Now I'd like to get it, I want to do energy. This is fantastic and extremely practical and useful. The fact that the energy is going to come out beautifully too. So what am I going to do for energy? I'm going to integrate f of x squared dx. That's the energy. That's the energy in x space, in the function. What do I do now? I integrate the series, ck e to the I kx squared. Oh no, whoa. If I put a square there, right, I'm fired, right? What do I have to do? I will put a square there, but I have to straighten out something. What do I do? Those curvy lines, which just meant take the thing in square, should be changed to straight. Just a matter of getting them straight, straightening this out. Okay, straight. There we are. Okay. Now that means the thing times its conjugate. That's the thing times its conjugate. So what do I get? All the terms disappear except the ones that are squared. So what do I get here? And the ones that are squared, I'm integrating 1, so I get a 2 pi. So there's a 2 pi. The whole subject's full of these 2 pi's and 2 pi's. It's just part of the deal. Now, what's left? Then now I'm looking only at the terms where I'm integrating something by its conjugate, by its own conjugate, and then I'm getting ck times its own conjugate. So I'm getting all the terms. I'm getting no cross terms, just the terms that come from that times its own conjugate, which is ck squared. That's the energy in the coefficients. That's the energy in k space. And of course, that sum goes minus infinity to infinity. I've got them all. That's the energy in k space. Here's the energy in x space. Yeah, yeah. You can expect that this orthogonality is going to give you something nice for the energy, for the integral of the square. All right, so you saw that, and let's see. So we saw it we actually got a good number for the square wave. We got infinity for the delta function. I've put on here as a last topic to just give the word function, tell you, part of what this course is doing is to speak the language, teach the language of applied math, so that when you see something, you see this, you recognize, hey, I've seen that word before. So I want to know what's the right space of functions. This is my measure for the length squared of a function. My square wave is great. Its length squared was whatever it was, pi squared over something, and that's its length squared. The delta function gave infinity. So it's not going to be allowed into the function space. It's a vector of infinite length, like the vector 1, 1, 1, 1, 1 forever. Too long. We can't sum. Pythagoras fails because we sum the squares, we get infinite. So what functions, what vectors should we allow in our space? So we're going to have a space. It's going to be infinite dimensional because our coefficients, we've got infinitely many coefficients. Our functions have infinitely many values. So we've moved up from n-dimensional space to infinite dimensional space. And everybody calls it after the guy Hilbert space. So I don't know if you've seen that word before, that name before, Hilbert space. It's the space of functions with finite energy, finite length. So this function is in it, the delta function is not in it. The point is that this space of functions, we've got these guys are a great basis for the space of functions. The sines and cosines are another basis for this space of functions. We just have a whole lot of functions. And all the facts of n-dimensional space, so what are important facts about n-dimensional space? One that comes to mind is that involves length is a key fact about length is length and angle. The key, I could say actually, many people would say this is the most important inequality in mathematics, that the dot product of two vectors, do you know what this it's called the Schwarz inequality? Several people found it independently. Schwarz is the single name most often used. what do you know about the dot product of two vectors? Somehow it tells you the angle between them, right? Somehow the dot product of two vectors is, if I divide by the length of the vectors, so the dot product of vectors divided by the length, do you know what this is in geometry? It's a cosine. It's the cosine of the angle between them. And cosines are never larger than 1. So this quantity here is never larger than 1. In other words, this is never larger than the length of one vector times the length of the other vector. Right. I could do an example. Let V be 1, 3. And let W be 1, 6. I don't know how this is going to work. What's the dot product of those two vectors? Oh, it's 19. Sorry about that. Let's change this to, I'd like a nice number here. What do you suggest? Make a 5 somewhere here? Oh yeah, 5 wouldn't be bad. 5 wouldn't be bad. Well, it wouldn't be too good either, but yeah. Let's do it. Okay, what's the dot product of those? 16. And now what am I claiming that that's length less than the length of this vector, which is what? What's the length of 1, 3? Square root of 10. It's good to do these small ones just to remember. The length of that vector is the sum of the square root of the sum of the squares, square root of 10. And the length of this guy is the square root of 26. And so I hope, and Schwartz hopes, that 16 is less than that square root. Can we check it? Well, let's square both sides. That would make it easier. So the right-hand side, when I square both sides, will be 260 when I square both sides. And what's the square of 16? 256. That was close. But it worked. Right. I'll admit to you whoops, not equal. Lesser equal, Schwartz would say, and it's actually less than because these vectors are not in the same direction. If they were exactly in the same direction or opposite directions, the cosine would be 1 and we would have equals. But since the angle, you see the angle between those two vectors is it's pretty small angle. The cosine is quite near 1, but it's not exactly 1. Yeah. So I'm glad somebody knew 16 squared. Does anybody know 99 squared? It was, the reason I asked that is, or 999, I'll make it sound harder. Was the hope when I was about 11 or something, I was always hoping somebody would ask me 999 squared because I was all ready with the answer. Nobody ever asked. Anyway, but you've asked, I think. So 998,001. And now I finally got a chance to show that I know it. Okay, have a great weekend. I'll see you. Okay.